Welcome, students. After today's lecture, you should be able to convert any longhand chemical structure into a line bond structure and draw resonance structures. Are you ready? Let's begin. Before going on, I have to explain something very important. We organic chemists use a shorthand way of drawing carbon-carbon bonds called line bond structures. The way this works is that instead of drawing the letter C for every single carbon atom, we instead draw a single point. Single bonds are then drawn as straight lines between 2 points, which are 2 carbon atoms. Double bonds are drawn as 2 straight lines, and so forth. Hydrogen atoms are not drawn. We instead assume that each carbon atom has as many hydrogen atoms as it needs added to it or bonded to it to attain 4 total bonds. All atoms other than carbon or hydrogen are written in as the atom's letter symbol. An old organic chemistry professor of mine in grad school once joked that to be an organic chemist, the only skill you need to have is to be able to count to at least 4. So let's look at these examples. In this first one we see this molecule that has 6 carbons here and a bunch of hydrogens. If we wanted to, we could draw every single carbon-carbon single bond and every carbon-hydrogen single bond. And when we were all done, we'd probably be really tired because we'd be drawing a bunch of bonds. Fortunately, chemists have devised a means of doing this in a much faster shorthand way called line bond structures. The way we would draw this molecule right here in a line bond structure format is like this. You'll note that each one of these points represents a carbon atom. There are 6 carbon atoms shown in the molecule to the left, and there are 6 carbon atoms shown in the molecule to the right. 1, 2, 3, 4, 5, 6. The hydrogen atoms are not drawn. So we assume that each carbon atom shown on the line bond structure to the right has as many hydrogen atoms necessary stuck to it as are needed to ensure that it has 4 total bonds. Here's another example. 6 carbon bonds in a ringed structure where every other bond is a double bond and all the ones in between are single bonds. Rather than draw this molecule this way, we can draw it this way. Note that each of these points represents a carbon atom, double or single bonded to its carbon atom neighbors. And then this example is where we have carbon-carbon bonds single bonded to each other and this carbon-oxygen double bond. We can draw this in this manner right here. Carbon-carbon singles, carbon-oxygen doubles, and no hydrogens. I hope that this is clear, the difference in comparison between longhand or calculus structures and line bond structures. This leads us perfectly into a beautiful lecture problem. Convert the following molecular formulas into line bond structures. You'll note that for some of these examples there are more than one possibility. In this example, draw line bond structures for the following molecules. I will let you do these problems on your own, but I hope that you will do them because they're excellent practice. We now diverge into another subject, that of resonance structures. Okay, so there are some molecules that have pi electrons that can move around from one atom to another. For example, the following molecules, A and B, are both different forms of acetate. Now look at this for a minute. You'll notice that in this form of acetate, molecule A, this oxygen has a minus charge on it, and this carbon is doubly bonded to the oxygen above it. Now if you can imagine this oxygen coming down here following the path of this arrow and closing in to form a double bond between this oxygen and this carbon. Upon doing so, it would thrust the pi electrons here up onto this oxygen. What happens then is now there's a carbon-oxygen double bond here, and these pi electrons that were formerly being shared are now up on this oxygen, giving it a negative charge. You'll note that structures A and B are called resonance structures. In reality, acetate actually exists somewhere in between A and B, with the negative charge being shared equally between the 2 oxygens. We sometimes draw acetate then like this. This is sort of like a way of showing that this negative charge is being smeared or shared between these 2 oxygen atoms. Drawing different resonance structures is kind of like moving doors on a hinge. To show you this, I'd like to show you a few resonance structures for a few different examples. Before getting to those, however, we need to cover a few resonance structure rules. I want you to remember that when you draw resonance structures, 1, only pi electrons, lone pair electrons, or negative charges can move. You don't move positive charges or other strange bonds. 2, you can move electrons toward or into an atom that does not have a full octet. And 3, you can only move electrons into an atom that already has a full octet if you have other electrons push out in the opposite direction. That is, electrons come in, electrons go out, if the atom in the middle already has a full octet. And 4, we do not break sigma bonds, only pi bonds. So let's take a look at some examples. In this example, we've got an oxygen here that has a negative charge and a nitrogen in the middle. It obviously has a full octet because it's got 2, 4, 6, 8 electrons around it, remembering that each line around it represents 2 electrons. This nitrogen has a positive charge not because it lacks a full octet, but because nitrogen, generally speaking, only wants to have 3 total bonds. So when it has 4 total bonds, that means that that nitrogen is sharing more electrons than it normally would want to. Hence, it gets a positive charge. Now note that if this electron, or these electrons right here from this oxygen, were pushed down, in other words, if we took one of these lone pairs and pushed it down into this nitrogen, we could form a nitrogen-oxygen double bond here. However, if we left those electrons there, the nitrogen would now have 10 electrons around it, violating the octet rule. How do we combat that? Well, what we do is we have one of these bonds thrust up onto this oxygen here. In doing so, this oxygen gets a formal negative charge here. So we can go back and forth between these 2 resonance structures, also called resonance contributors for this molecule. We would say that the molecule in reality is somewhere in between, and we could draw that by drawing dotted lines between the nitrogen and the 2 oxygen atoms and drawing a partial negative charge at each oxygen atom. This indicates that this negative charge is being shared or smeared across both oxygen atoms. We call this molecule the resonance hybrid, which is once again recognizing that in reality this molecule exists somewhere in between these 2 different resonance contributors. Here are some other examples. If I wanted to take the carbon-oxygen pi electrons here in this double bond, I could thrust them up onto this oxygen, and doing so would give this oxygen a negative charge. This carbon, because it just lost 2 electrons in this interaction, now becomes positively charged and lacks a full octet. In this example, you'll note that we've got a positively charged carbon here. Now what that means is that this carbon only has 6 electrons around it. I can have these pi electrons swing like a door on a hinge. Now if you can imagine having a bird's eye view looking over a door, if the hinge of the door were right here, this door could swing open and close. If it closes on this carbon right here, there's now a carbon-carbon double bond here, but this carbon over here to the left formerly did have access to these 2 electrons, and now it lost that. So it has now got a formal positive charge. So it is now electron deficient. In reality, this molecule exists in a state that's somewhere in between these 2 resonance structures. By comparison, now I have a carbon that has a negative charge on it. This carbon does not lack a full octet. In fact, what it has is 2 lone pair electrons. That's why it has a formal negative charge. These lone pair electrons could thrust into here, forming a carbon-carbon double bond. But if we did that and just left that carbon-carbon double bond, this central carbon would have 10 electrons around it. 2, 4, 6, 8, 10. So what has to happen? Electrons have to thrust back out and onto this carbon, giving this carbon a formal negative charge. Hence, this is one of those circumstances where electrons go in and electrons come out. In reality, the molecule exists somewhere in between these 2 resonance structures. Here are a few examples. You can see that this example here, the molecule known as benzene, each of these different pi electrons can swing like a door on a hinge, closing to form a double bond, and then swinging the next pi electrons to closing to form the next double bond. This gives this resonance structure shown to the right. Similarly, if I have these pi electrons thrust here, they close to form a carbon-carbon double bond, but I can't leave that because if I did, this carbon would have 10 electrons around it. Hence, these pi electrons have to thrust up onto this oxygen, giving a negative charge. Because this carbon over here to the left lost these 2 electrons that it formerly had access to, it now has a positive charge and only has 6 electrons around it. Hence it has less than a full octet. Here's another example, very similar to the one we saw earlier. If I have lone pair electrons from this oxygen thrusting down here and closing like a door on a hinge, it closes that trapdoor to give me a nitrogen-oxygen double bond, but I can't leave that because doing so would give that nitrogen 10 electrons around it. Hence, this process has to require these 2 pi electrons to come up onto this oxygen, giving it a formal negative charge. Hence, these are 2 resonance contributors of this molecule. This leads us to a beautiful lecture question. Which of the following structures represents a correct resonance structure for molecule A? In order to answer this, I'm going to take a look at these hand-drawn structures that I've done myself. Note that this nitrogen has electrons on it, and they are lone pair electrons, and in resonance structures, lone pair electrons and pi electrons can move. So I could have these lone pair electrons swing in and close to form a nitrogen-carbon double bond right here. I can't leave that, however, because if I did so, this carbon atom right here would have 10 electrons around it. Hence, if these electrons from the nitrogen thrust in, pi electrons between this carbon and oxygen have to thrust out. In doing so, they give this oxygen a formal negative charge. The nitrogen has a formal positive charge in this scenario, not because it lacks a full octet, but because nitrogen with 4 bonds around it always has a positive charge, because that nitrogen is sharing more electrons than it normally likes to. Nitrogen, to have a neutral charge, wants to just have 3 bonds around it. Now you might ask, why in the world couldn't I have electrons from this oxygen thrust down to form an oxygen-carbon triple bond? The only way we could do that is if I broke this carbon-nitrogen single bond and thrust the electrons out to this nitrogen. Doing so would violate one of our rules, and that is the rule that says that we do not break sigma bonds. We only break pi bonds when we draw resonance structures. Remember, single bonds are sigma bonds, whereas one of the extra double or triple bonds are indeed pi bonds. So this brings us to our final lecture question for this video. I want you to draw the 3 different resonance contributors, also called resonance structures, of phosphate, PO4-3, whose structure is shown here. In order to answer that, I'm going to show you these hand-drawn structures I have here. We could imagine this oxygen atom right here, which has a negative charge on it, thrusting that negative charge in, closing a bond between it and the phosphorus atom here to form a phosphorus-oxygen double bond. In doing so, however, we have to thrust these 2 electrons up onto this oxygen. Now you'll note, looking at this, that the phosphorus atom actually has 10 electrons around it. It violates the octet rule. How can phosphorus do that? The answer is because phosphorus is in the 3rd row of the periodic table. Hence, it has more orbitals that allow it to be able to obtain a hyperoctet. Nevertheless, we are going to retain only 5 bonds to our phosphorus instead of having more than 5 bonds in every one of these resonance contributors. When this oxygen thrusts its electrons down to close this door, forming a phosphorus-oxygen double bond, doing so causes these electrons to thrust up onto this oxygen, giving me this resonance contributor. Where do we go from here? Well, one direction we could go is we could have this oxygen negative charge down here thrust its electrons in, closing to form an oxygen-phosphorus double bond, but in doing so, it will also thrust these pi electrons up onto this oxygen to give me this resonance contributor. Where can we go now? Well, I'll just follow suit and have this oxygen right here thrust its negative charge electrons onto that position, forming an oxygen-phosphorus double bond, and pushing these 2 out, forming this resonance contributor here. And where do we go next? Well, we can have these electrons come down here to form a phosphorus-oxygen double bond, pushing these back, and you'll note that doing so returns us back to the very original resonance structure that we started with. Hence, the 3 structures that might be asked for in these questions are the ones indicated here. So that brings us to the end of our first lecture on an introduction to organic molecules. I hope that you enjoyed it, and I hope that you'll stay tuned for our next lecture, in which we'll talk about a wide variety of additional subjects, delving deeply into the wondrous world of organic chemistry. Until then, have an enjoyable day.